All right, so let's take a look at 8.4. This is about logarithmic functions. We're going to look at the definition of what a logarithmic function is. We're going to evaluate logarithmic expressions. We're going to discuss what the common log function is. We're going to look at the graphs, and we'll look at some applications for logarithmic functions. So let's start by looking here. And it says here that if x and b are positive real numbers such that b does not equal 1, then y equals log base b of x is called the logarithmic function with a base of b, and I'm going to put this, let's see, I'm going to write out so I'm going to color code this. They'll make more sense in a minute. So if you have y equals log base b of x, it is equivalent to the base raised to the y power is equal to x. So these are two equivalent statements. So when you see this, I want you to think, okay, this is base b. I can rewrite it in exponential form by taking the base, raising it to the y power, and set it equal to the argument. So in a logarithmic expression, y is called the logarithm. B is called the base, and x is called the argument. So this is a logarithmic expression or an equation function, and you can rewrite it as an exponential function by taking the base, raise it to the y, and set it equal to the x. So I like to draw these little arrows out when I'm trying to convert it. The expression y equals log base b is called the logarithm form. And the expression b to the y equals x is called the exponential form of the equation. A logarithmic function is the inverse of the corresponding exponential function. Rewrite the logarithmic equations in exponential form. So here we have a logarithmic equation, and we're going to say, and I know they put those little bubbles in, but I would suggest take the base, raise it to this exponent, and set it equal to the argument. So this is the same as this. Here we have 2 to the third power. So they're drawing an arrow too. This is from the book, but I kind of stop my arrow. I stop it and I say 2, and I put the little caret symbol so that I remember I got it. That's the exponent. And then this would be the answer. So they draw it all in one swoosh, which you could, but I kind of stop it in between so that I remember this is exponent, this is equals. So we have these to try. So I'd like you to try pausing and then try doing these problems and then restart the video. All right, so let's try them. 2 to the third power is equal to 8. This is actually the same one that we saw up above. Here, the base raised to the fourth power is equal to 81. And you'll notice that these are true statements. 2 to the negative 2 power is equal to 1/4. And that's also a true statement, because when I have when I have a negative exponent, it goes to the bottom and becomes 1/2 squared, which is 1/4. Evaluate the logarithmic function. So here, in order to evaluate them, what I'm going to do is first rewrite them in exponential form. So if I'm going to rewrite them, that means that, and I'll just rewrite it on the underneath it. 4 to, I'm going to call this my unknown, or x. So 4 to the x power is equal to 64. So I asked myself, well, what power does 4 need to be raised to equal 64? And I could think of the powers of 4. 4 to the first is 4. 4 squared is 16. 4 cubed is 64. You can put those in the calculator to verify. So that means that the value of x would be 3. The next one, I would say 7 to the x power is equal to 1/49. So 7 to the x is equal to 1/49. Now, let's rewrite this. I'm going to show you another way to think of this. 1/49 would be the same as 49 to the negative first power. 49 is 7 squared. So I get 7 to the x, this is a power raised to a power, is equal to negative 7 to the negative second power. And when you have the same base raised to a power, the powers have to be equal. So the missing part here is negative 2. There's a property with logarithms where if you have, here, let me write it like this. If I have x to the m is equal to x to the n, if this is true, if the bases are the same, they're both x, then the two exponents have to be equal. So you can use that property when evaluating log expressions, especially in a situation like this. The next one here, 5 raised to something is equal to the square root of 5. So 5 to the x power is equal to the square root of 5. Well, I can rewrite this base. This is the square root is the same as the rational exponent 1/2. So here I get 1/2 as my answer. So you should try pausing the video and try the ones that remain and see what you get for those, and then unpause and watch how I do them. Letter D, 2 to the x power is equal to the 5th root of 2. So I get this statement. Now, what I was saying in part C was that you can rewrite the roots as a rational exponent, whatever the index is here. So this is a square root. There's an index of 2, but it's not written. That becomes the denominator. And you say 1 over the index. So the value of x here would be 1/5. The next one, I've got 4 to the x power is equal to 4 to the 9. Bases are the same. The exponents have to be equal. So here's my answer. And then the last one, let's call this x. B to the x power has to equal b to the 75th. So because the bases match, they're both b, I can say x equals 75. So their exponents would have to match. Scrolling down, we'll see that the logarithm function with a base of 10. So in the ones that we have seen up here, none of these had a base of 10. If you have a base of 10, a base 10 is called the common log function, and it's denoted like this. So just the log x. Log x is known to be a base of 10. So it's not explicitly written, but it is understood to be 10. So this is the same as this. And so if I wanted to evaluate these logarithmic expressions, well, just imagine what the base is here. Well, the base would be 10, caret symbol, x is equal to 10,000. So 10 to the x equals 10,000. And I can rewrite the base of 10,000. I can rewrite these to have the same base. 10,000 is a power of 10. It's 10 to the 4th. And if you don't recognize that, you can just think, you can put it in your calculator and see 10 to the 1st is 10, 10 squared is 100. And you kind of will see the pattern here. Each time you raise the power, another power of 10, it attaches a 0. So 10 to the 4th would be 10,000. So that means that my exponent, or my answer here, would be 4. The next one, there's a base of 10 here, so I'm going to say 10 to the x equals 0.00001. Now this one we haven't seen before, but this is a power of 10 also, but it has a power, it has a negative. If we were to rewrite this, 1, 2, 3, 4, 5, that is the same as saying 10 to the negative 5th power. I meant to write x here. Because it is taking, and we can rewrite this in kind of a scientific notation. So the missing value here would be x to the negative 5. And then the last one, base of 10 is equal to the answer. Raised to the answer is equal to 1 over 1,000. So I'm going to say 10 to the x is the same as 1 over 1,000. Well, 10 to the x, rewrite this, that would be 10,000 to the negative 1st power. And then rewrite the 1,000 to the negative 1st power. And rewrite the 1,000, it would be 10 cubed. And a power raised to a power, you multiply those exponents to get 10 to the negative 3rd. So the missing value here would be negative 3. The next one says to evaluate the common logarithms around your answers to 4 decimal places. So when you look at the calculator, you will see the log key on here. The log key is right here. On other calculators, it will be somewhere similar, but it will always say log. And log means the common logarithm. So when I type this, notice the base doesn't show up. It just says log and then a parenthesis. So this is, the calculator has a common logarithm built into it. And so on this one, I end up with 2.3979. It says to round to 4 decimal places. So that means I would have 2.3979. The next number was less than 5, so I keep this 9 the same. The next one, .3902. And then the last one, we'll do log 2.4. This is a scientific notation, so to get that in the calculator, hit second comma, and then put the exponent. The exponent here is 4. And we'll get our answer to be 4.3802.